We're going to now look at the factors that impact delta H of solution, because in solution formation, the entropy factor is fairly predictable. It's really the delta H component that we need to investigate a little bit further. Right now, we're going to focus on covalent solutes, and then in the next section, we're going to focus on ionic solutes. So in solution formation, if you think about what happens when a solution forms, you have solute that are packed together, and then you have solvent that are also packed fairly close together, usually in a liquid form. And then we are trying to combine the two of these things together so that we form a solution where the solute and the solvent are intermingling, right? They're mixing together like this. Okay, so there's really a couple of steps that we need to do in order to make that process happen. And the steps are illustrated here. So in step 1, what we need to do is we need to separate out the solute particles from each other. We need to make room, in other words, for the solvent to be able to get in there, right? And so that means breaking intermolecular interactions, or whatever intermolecular force is holding those solute particles together, and getting it into the separated state. So the way we can think about the reaction is we take solute from the aggregated, or the sort of the tightly packed state, into the separated solute. Now, that process is going to be endothermic, so the delta H of solute is positive. Okay, you need to do the same with the solvent, right? The solvent are also interacting with itself, right? All the solvent particles are making whatever intermolecular interactions it's making. Could be hydrogen bonding, could be dipole-dipole, whatever it is. They also need to be separated to make room for the solute to come in. So same type of reaction, the solvent in the aggregated state going to the solvent in the free or separated state. That process is also going to be endothermic. Delta H of solvent is going to be positive. So we call those delta H of solute, is the delta H needed to break apart that interaction for solutes, and then for solvent, we call it delta H of solvent. Now, after both of them are separated, we can then combine them together into a mixture of solvent and solute. Now, the solvent and the solute is going to make their own new intermolecular interactions. So I'm illustrating it here as these black dots, right? They're connecting the solute and the solvent, okay? And so those are new intermolecular forces, and we call that delta H of mixing, and that number is going to be negative because, again, you're making interaction now. So when you're breaking interaction, you need to put an energy. When you're making interaction, you're lowering the overall energy of the system, so that process is exothermic. So the delta H of the solution, which is the number we calculated earlier in the earlier section when we discussed this, right, is really the sum of these three components of the solution formation: the delta H of solute, the delta H of solvent, and the delta H of mix. And these two are endothermic, and the delta H of mix is exothermic. So here I'm showing you a picture of what the process looks like. This is step 1, where you take the solute that's tightly packed into the separated solute. Here's step 2, where you take the solvent and expand it or separate it, and then the separated species are then combined together to form our step 3 system, which is the mixture of the solute and the solvent. And so if we want to analyze values of delta H of solution, there's 3 different components in that delta H of solution. Now, what are the possibilities for the value of delta H of solution? Well, one possibility is the delta H of solution is 0, or a number that is pretty close to 0. And again, this will happen if you think about the delta H of solution being composed by delta H of solute, delta H of solvent, and delta H of mix, with these two being positive and this one being negative. You will get a delta H of solution close to 0 if the delta H of mix has an absolute value that is about the same as the sum of these two numbers. If you think about what that's telling you, that's basically saying that whatever intermolecular interactions that happen between solute and solvent in the mixed state is going to be relatively the same as the intermolecular interaction that happens between solute and solvent and solvent. So in other words, the solute and the solvent are fairly similar chemically, so that they're able to make very similar interactions. This typically happens when you have, again, two things that are very similar. So it will generally happen when you have two nonpolar solutions. They're about the same size. So here I'm giving two hydrocarbons, hexane, which is C6H14, and benzene, which is C6H6. So these two molecules have fairly similar polarity. They're just hydrocarbon. They all only contain carbon and hydrogen. They're nonpolar. And so they mix pretty much with that type of profile of delta H of solution being close to zero. When we have solutions like this is what we refer to as an ideal solution. I don't want you to give some strange idea about the word ideal here. It's the same as when we talk about the ideal gas. There are certain simplifications that we can make when we're dealing with ideal solutions. And that's the reason why chemists like to work with them, because certain calculations are a lot easier to do for ideal solutions versus non-ideal solutions. Now let's take a look at the other two possibilities. We could have a delta H of solution that is negative, which means we have an exothermic solution. Energy drops when you mix the solvent and the solute. Okay, this will happen again if you look at that top equation there. It will only happen, the whole thing will be negative if the delta H of mix, which is the negative number there, is bigger in absolute value than the sum of the other two numbers, right? And so that's what I wrote here. So what this is telling you, again, going back to this picture, is to imagine what happens. That's telling you that this interactions in the mixed state, which is between the solvent and solute, is somehow a lot stronger than the interaction that originally exists in the solute alone and the solvent alone. Okay, so this usually happens when you have hydrogen bonding that appears in the mixed state, but it maybe didn't appear in the separated states, in the solvent and solute states. Or maybe the hydrogen bonding is a lot stronger when it's in the mixed state versus in the solvent and solute state. Okay, so an example of this is a solution of acetone, which has that formula and has a dipole-dipole interaction. So the molecule itself looks like this, with chloroform, which looks something like this. Okay, also has a dipole-dipole. But then when you combine them, the dipole-dipole gets stronger than the dipole-dipole that exists previously when it was just the solvent and the solute by themselves. Okay. When you have this kind of a solution, we call it a non-ideal solution. Basically anything where the delta H is not exactly zero or close to zero, then we call it a non-ideal solution. So this is one example of a non-ideal solution. It's an exothermic solution. We can also have an endothermic solution, which is where the delta H of solution is positive. In this case, just to use the same reasoning, your delta H of mix now would have to be smaller in absolute value compared to the sum of the other two numbers, such that you get a positive number when you add all three numbers together. This must mean that that interaction that you have in the mixture is now weaker than what you originally have in your solute-solute and in your solvent-solvent. Okay, so this is sort of the opposite case from number 2 that we just talked about. And an example of this is if you, for example, have acetone, which again is a dipole-dipole type molecule, with carbon disulfide, which is actually a nonpolar molecule. So because one is polar, that's why it has dipole-dipole, and the other one is nonpolar, they don't really make very strong interaction with each other. They actually prefer to be in their solvent state and solute state as opposed to be in the mixed state. And this is just another example of a non-ideal solution. In this case, it's non-ideal because the delta H is positive. Okay. Now, these type of solutions still forms because the entropy a lot of times is able to overcome that unfavorable delta H that we have. So this energy diagram actually shows you how these processes happen for both types of solution, the exothermic and the endothermic solution. So again, for the exothermic here, we start with the solvent and we separate it out. We start with the solid, we separate it out. Both of these processes are endothermic. That's why you see we start from here and then it goes up and then it goes up some more. So both these numbers are positive, right? So the number goes up. And then now you're at this unstable state. But then when you mix the two things together, you gain all these energy back plus some more. So then it drops all the way down here. So the solution state is a lot lower than the other two. And so you get your delta H when you add these two numbers here, and then with that mixing number, you get a negative number overall, which is what this green arrow is representing. So it tells you that the delta H is going to be negative. With the endothermic solution, processes are the same. You break apart the solvent, you break apart the solute. But in this case, you can see that the step to break apart that solute is just a lot more endothermic. So maybe the interaction originally that exists there is much stronger. So you need to put a lot of energy to break it. And then when you mix the two things together, you still gain that reduction in energy, but it's just not as much as what you lose. So in the end, we get this green arrow to show you that the delta H is actually positive. So will solutions always form? Well, the answer is not always, right? So it depends, again, in the end, always on the value of the delta G of solution. So if the delta G of solution is negative, then you will have a spontaneous formation of your solution, whereas if the delta G of the solution is positive, then the solution doesn't form. Okay, and of course, right now we're only focusing on the delta H of solution, but there's always that entropy factor, and the entropy factor is going to tell you when you add it with the delta H of solution whether a solution will form or not. Okay, so sometimes instead of calculating the delta H and delta S of solution, we use this simple rule of predicting whether a solution will form or not, and that's called like dissolves like. This is particularly applicable for things that are really large. So for smaller molecules, it's easier usually to do those calculations like what we did in the previous section. But as you get larger and larger, it's just harder to measure those numbers very precisely, the thermodynamic values. So for this, we typically just look at how many polar groups, which are usually OH group, NH group, or CO group, right? These are all polar group. How many of those are there relative to the nonpolar groups, which is typically the CH group. Given whether we have a lot more polar or a lot more nonpolar, we can make prediction about the solution formation. If we're mixing with water, water is polar, so if we're mixing something that's nonpolar or mostly nonpolar, then we know that it's not going to mix. If we have something that's fairly polar, then we know it's going to mix pretty well. So here's an example. It's asking you if a solution will form or not in each of these following mixtures. So the first one is ethyl alcohol, which has this formula right here, and water. So this molecule has a OH group, as you can see. So it's CH3, CH2, and then OH. So that OH can hydrogen bond with water. It's a function of how long this hydrocarbon chain is, because those are the nonpolar parts. But in this case, since the molecule is small enough, solution can still form because there's still a potential for hydrogen bonding. Now, what about if I have these two hydrocarbons? This is hexane and this is octane. This also will form a solution because they're both nonpolar. Since they're both nonpolar, they will actually both have London dispersion forces, so they're going to be able to maintain that interaction in the solid-solvent state as well as in the solution state. Now, if you have octane and water, this is when you're not going to have a solution, okay? And it doesn't form because you have a nonpolar molecule and a polar molecule, and they don't really want to mix, okay? And so that's kind of how you think about whether mixing will happen or not, just based on polarity. If you can't really calculate your delta H of solution the same way as we did, at the very beginning of this chapter. Here's another example. We're asked to rank the relative solubility of the three compounds that are shown below. These are all shown as line diagrams or line structures, which is a common tool to illustrate organic molecules. So I want to remind you, something you should learn in Gen Chem 1 is that when you have these line structures, each of the line represents a bond. So like that line there represents a bond. And then when you draw something like this, the line basically ends at a carbon atom. So there's, in other words, when I draw a line structure like that, it's saying that there's carbon with another carbon, and then there's hydrogens attached to each carbon such that it satisfies the octet rule. So you need 4 bonds to make that happen. So CH3 here, CH2, and CH3. So that's what these two structures are, identical structure. But the key here is when we want to determine relative solubilities, and since they don't specify, we're really trying to figure out relative solubilities in water. What we have to do is just figure out how many polar groups and how many nonpolar groups are present. So if you look at the length of the chain, you can count this. So this one is 1 carbon, 2, 3, 4, and 5 carbon, okay? And then this one is 1, 2, 3, 4, and 5, and 6, actually, a little longer. And this one is 1, 2, 3, 4, 5, 6, 7, 8, okay? So you can see that the more carbon CH groups you have, usually the less polar it is. But then the more OH and NH and CO type groups you have, the more polar it is. So in this one, I have 3 of these polar groups. Also not mentioning that the CO is here. There's a CO here. Those are polar. Okay. With the second one, I have 2 of these polar groups, and the third one, I also have 2 of these polar groups. So for sure, the first one, it has the fewest number of nonpolar groups, only 5 carbon in there, 5 carbon hydrogen type groups, and 3 of the polar groups. So this is the most soluble of the 3. And then when you look at the other 2, they both have the same number of polar groups, right? They both have 2 polar groups. But then the last one is a longer chain of carbon. So that one is going to be more nonpolar, so then least soluble. And then the middle one is the one that is in between the solubility of the 2 other ones.